chapter, and if you haven't, you need to, because there's really two main types of sampling that we're going to talk about. One deals with means and averages, and that's what we're going to talk about today. And then there's another thing that talks about proportions and percentages, and we can really talk about, so we have means and proportions, and there's two separate types of formulas going on with each of those for standard deviation. And it's important to know both, okay? So we're only going to talk about means today, and then next class we'll talk about proportions, but they do have completely different formulas and different conditions, and we'll talk about what that means here in just a second, okay? But I think we kind of ended up here in last class where we talked about the NFL sticks and continuing to take samples and what really happens when we graph the means of those over time. And we kind of looked and we looked over here. We said, well, it gets definitely more mound shaped. Now this only had a sample size of 15, if you remember, and we really have to get larger. Does anybody remember what the magic number was we talked about? 30. So 30. Some textbooks it's as high as 40, anywhere from 30 to 40, but the good rule of thumb is at least 30. And you'll actually be pretty surprised that if we were to take samples of size 30 and graph the averages over and over, they really would become normally distributed, which is kind of what the central limit theorem says. Got a question for us?
Like the 30, like the equals 30, is that like for every amount of stuff? Or like for
the sample size, it has to be of at least 30 in order for it to qualify for the central limit theorem. In order for the central limit theorem to apply, we really have to have it's one of the conditions that we're going to check. And I believe that, we're going to watch a giraffe video in a minute too. Yay. Well, let's actually watch the giraffe video. But we there are some conditions that we're going to check. And like again, when we're talking about means and averages, there's a set of conditions for those, and there's a separate set of conditions for the proportions. But one of the conditions for means and sample size has to be, we call it large enough sample size, and n is greater than 30.
like for a population of any size?
Yeah, any size. Any size. Even if you have a size like 3 trillion. Yeah, 30. Yeah, I mean, honestly, the sample size, well, you can't have something too large also. It has to be less than 10% of the population. So you can't do a sample size of 30 and have a population of 50. A population of 50, there's no need to sample, right? So you have to have a large enough population for it to less than 10%. So again, we're going to get to those conditions in a few minutes too. But that is one of the conditions also. Less than 10%, greater than 30. Okay? All right, so let's look at this giraffe video. I have a little video I found that really talks about the central limit theorem and maybe kind of summarizes it for us. So if you would you hit the lights for us, Judith? Thank you. I don't know if you guys have ever done any of the Discovery education. They do stream them, and they tend to sometimes they buffer and tend to stop every once in a while. So just be patient. Hopefully it won't do that. I tried to log into it early enough, but we'll see. So I'm going to put the microphone kind of up to the speakers, and hopefully you'll be able to hear it through the video too. I did push play, right? Okay. Groovy music, just so you know. Digging it.
Often called the watchtowers of the Serengeti, giraffes are the tallest mammals on Earth. The tallest giraffes reach heights of over 18 feet. Not all giraffes are this tall, but you can get a good idea of the heights of giraffes across the Serengeti by sampling. If you knew the height of every adult male giraffe in Africa, you could graph the frequencies of these heights. The graph might look something like this. Notice that the curve approximates a bell shape. In nature, graphs illustrating distributions of frequencies of measured characteristics in large populations often have a special kind of bell shape like this one. This is called a normal distribution. The tallest part of the curve represents the height you would expect to find most often, and around which the measurements would tend to cluster. For normal distributions, this is both the mean, or average value, and the median. The tails of the curve extending in both directions represent the decreasing numbers of giraffes that are much taller or shorter than most adult giraffes. It would be impractical, even impossible, to record every giraffe's height. However, by looking at a random sample of giraffes, we can get an idea of the distribution of heights in the whole population without measuring every giraffe. For the sample to represent the distribution of heights in the population well, two features of the sample are important: randomness and size. With a random sample, any giraffe in the population is equally likely to be included. Also, the sample size, how many giraffes are in it, is important. The larger the sample, the more likely it is that it will accurately represent the population. Suppose we measure heights of a sample of 10 giraffes. A random sample of 10 giraffes from the thousands of giraffes roaming the Serengeti could give a good idea of how tall the typical giraffe is, and its mean provides an estimate of the mean height for the population. In fact, it is more likely to be a good estimate than the height of just one randomly chosen giraffe. You can see how this works if you compare means of samples with individual measurements. First, notice the amount of variability among these 10 measurements of single giraffes. But if you now plot the frequencies of the means of such random samples of 10, the means are closer to each other than the single measurements were, and each one is therefore more likely to be nearer the population's mean height. Increasing the sample size even more further decreases the variability in the sample means. If you took a sample of 100 measurements, the mean of that sample would be even more likely to be near the mean for the population. In this histogram, 10 means, each of 100 giraffes' heights, are so close together that they're all in one bar. You can see that you're even more likely to get a closer estimate of the actual mean height of all the giraffes from such a large sample. These means also tend to be normally distributed, but with even less variation. The tendency for sample means to be normally distributed, varying less with greater sample sizes, is the main idea of the central limit theorem. In fact, the means will tend to be normally distributed, even if the values used to calculate the means are not.
So even if the population itself is not normal, the means will be normal. And I don't think it was really emphasized heavily enough that when you have your sample size of a certain size and you're graphing the means, what happens to the standard deviation, the spread, the variability? What happens to it when you saw the graph? It got smaller, right? So when you have a sample size that's large enough, and your standard deviation, which is the way we measure variability, right, is going to be smaller when you're talking about the mean. Okay? And I'm going to show you the formula that gives you a smaller standard deviation in a couple of minutes. Okay?
With the distribution of means of 30 ages from the population. The population ages are not normally distributed, but the means tend to be. And this means a better understanding of the central limit theorem.
Anyway, I thought that was kind of an interesting little video, a really short kind of a clip that talks about the central limit theorem and an idea. Thanks, student. In terms of a context, so it's kind of an interesting way to look at it. Now, in those, they talked about the heights of giraffes, which were normally distributed to begin with. At the end, they kind of threw in a little bit the ages of elephants. Did you see that one? And that one was more of a skewed right graph. And when we talk about the age of an elephant, if we're talking about the population, much like our population of NFL salaries was very much skewed right. Once we look at the population, that's great. Once we start taking samples and graph the means or the averages of those samples, it's those averages that tend to become more normally distributed. And that's important because we know how to use normal, don't we? We know what normal CDF does on our calculator. What does it actually do? It calculates what for us? It calculates what? Cumulative probabilities, right? So if we're trying to find how likely something is to happen, we can use that distribution to find those probabilities. And that's useful for us, and that's what we're actually going to do. So as we draw more and more samples, the sampling distribution becomes more normal. And here's the key. And centered, let me write this down here, and centered at the actual population parameter. Now, it could be a mean or it could be a proportion. And again, today we're going to talk about means. On Wednesday, we're going to talk about proportions. Okay? But if we took all possible samples, let's think about the giraffes, and since that's the context that we're using right now. If I took, the sample size was 10, wasn't it, that they used on the board in the video? So if we took all possible different combinations of 10, well, how likely is that going to happen? But it's not really, right? But all possible ones, we would actually have the normal curve. We would have a really good, solid normal curve for us. Now, obviously, that's not possible to do all the different possible combinations. Would you agree? So we're going to take some samples of 10, and they will become more and more normal as long as the sample size is large enough. Okay? Now, here is the formula I was referring to earlier. Okay? This is a formula for standard deviation. So if you had a sample size of at least 30, and we know that the central limit theorem is going to apply, I'll give you the conditions we check in a minute. This is going to be our new standard deviation. Okay? It's the given standard deviation of the population divided by the square root of the sample size. So this is going to be the population standard deviation, and this is going to be the sample size. Okay? So if you are dividing your given population standard deviation by a number, aren't we going to get smaller? Our variation will decrease. And the larger the sample size we have, the smaller it's going to get. Okay? And that's a good thing. So here is, again, the formulas, which you just wrote down. Okay? The mean is simply going to be the population mean. Notice the notation. This says the mean of the means. Okay? Remember that mu, that Greek letter mu, means population mean. Do you agree? Sometimes we write it as a subscript. The mean of the averages. Maybe it's better if I say it that way. Okay, remember what we did. Those little dots on it's kind of hard to wrap your brain around sometimes. Every little sticker on that graph for NFL salaries, every one of these anyway, not the population, but either of the other two, it represents an average. So the mean of the averages, okay, is simply going to be the population mean. So it's centered about the actual mean, and we did this last class. We estimated the mean of the NFL salary somewhere right in here. Would you agree? Approximately, something like that. The standard deviation is just going to be your given population standard deviation divided by the square root of n. Okay? Now, oftentimes, we don't know the population standard deviation. Okay? We would know it for the NFL salaries. It's a small enough population where we could find a standard deviation. But when we talk about the heights of the giraffes on the Serengeti, is it possible to know the actual standard deviation of the population? No. So we can't. So we have to estimate it with the sample standard deviation that we collect. When that happens, and it's not possible for us to actually know what this number is, we substitute it with the sample, the one that we collected. Okay? When that happens, we call it the standard error, as opposed to the standard deviation. And sometimes the formula is written this way: the standard error divided by the square root of n. Okay? And that just means we just don't have a population standard deviation that we can use, so we're just going to use our given one, or our sample one. Okay? Did you guys read about the standard error in chapter 16, I hope? Okay, good. Or actually, was it 18? Yeah, 18. All right, good. So here are the conditions that we need to look at when we talk about the means Okay, now again, this applies for the means or the averages. And it will always be one of those two things. Okay, really from here on out for the rest of the year, you're going to make a decision. Is the question I'm looking at talking about averages, or is it talking about proportions? Okay, and we're going to, again, today is focusing on averages. The three conditions that we need to look at are these three. Okay? These are the three conditions you need. Yeah, absolutely. And the unfortunate part of the rest of the year, almost, is that everything we do from here on out is going to have a set of conditions that you need to check. And they're almost always different. So you're going to have to kind of, I hate to use the word memorize, but yeah. Okay? So we might want to start thinking about making kind of a little bit of an org chart, so to speak, okay? And first things first, if it says means, we're over here. If it says proportions, we're over here, okay? And then once we're in means, we're going to look at these three conditions for now. Once we're in means, we have lots of other tests that we can apply, and we'll talk about that in the coming weeks. But for now, two branches to my tree. Here are the first three questions on the means branch, okay? Random sampling condition, okay? We have to make sure that the sample was collected in a random fashion. Think about your NFL salaries. Was that a random sample? Did I go and mix the box up before you came into class and you randomly took out 10? Do you agree? Now, the problem I have with the way we collected our data is what? It was sort of random. There was an issue with it. Can you think of what the issue was? Yeah, we didn't replace it first, right? So Hunter took his 10, and in order for it to be a true sample, he should have put his 10 back in, we mix it up, and then Maddie would come get her 10. Find her average, put them back in, and so forth. What's the problem with that? We would be here in June and we still wouldn't have a graph, so we had to do the best we could with that information. Okay, so it has to be collected randomly, and oftentimes we have to assume this condition because it doesn't state how the data was collected. So what you will do is, when I say check your conditions, which I'm going to have you do almost always, you're going to say 1, 2, 3. 1, random, question mark. And if it doesn't say in the problem that it was collected randomly, you have to say, we assume the data was collected randomly. And you just have to assume that condition. And that happens sometimes. Number 2 is the independence condition. And this is kind of what I was just talking about. Were the sticks with replacement, were they independent of one another? Not in our case. Okay? So if they were dependent, great. If not, we have to do something called the 10% condition. So if we don't know that the samples were collected independently of one another, then we're going to use something called the 10% condition instead. Okay? And the 10% condition simply means that the sample size is less than 10% of the population. So in our case with the NFL salaries and the sticks, they weren't collected independently of each other. However, the sample size, the largest sample size we got was 15. Is 15 less than 10% of the population? Sure, there's definitely more than 150 players in the NFL, correct? I think each team has 50-some players, 52, 53, something like that. Okay? So definitely, so we met that condition. And then I erased. There we go. The last condition is called the large enough condition, okay? And this one is a little harder to satisfy. If you are told that your population is normal, the heights of giraffes, we know the heights of giraffes is already normally distributed. Therefore, we don't care what the sample size was. That's important. I'm going to say that again. Stop writing and listen for me, please. Okay? If the population, we are told that it's normal to begin with, I don't care what the sample size is. We can still use the central limit theorem. Okay? We can still find our new standard deviation and divide by the square root of our sample size. However, if we don't know anything about the population, or we definitely do know that the population was skewed in some way, much like the NFL salaries was skewed in some way, then sample size is going to matter. If the distribution is not normal, which obviously the population of NFL salaries was very heavily skewed, as long as your sample size is greater than 30, we can use the central limit theorem. So this condition can be met in two ways. One, the population itself is already normally distributed. Done. Check. Move on. And that's what you would say. Large enough sample condition. The population is normally distributed, therefore the CLT applies. Done. If we don't know about the population, then we have to look at the greater than 30. Okay? And usually it's greater than or equal to 30. I think 30 is good enough. If it's close, 29, we would say something like proceed with caution. So if any of these three conditions are not met, we would simply use the words proceed with caution, and we would continue on doing it anyway. But you have like a red flag out there that says, you got to be careful about this, because I didn't meet this condition. Okay? Number two, you have to know what the population size is. So if we talk about heights of giraffes and we had a sample size of 10, 10% of 10, I'm sorry, 10 is 10% of 100. We know there's more than 100 giraffes out there in the Serengeti, right? So that's where we'd be okay. Okay? And so we'll look at watch the giraffe video. That's funny. Okay, next. All right, so we can apply the normal modeling, which we want. So let's do an example. Okay, let's actually try one and see what happens here. So read this example to yourself, and I want you to first think about the conditions that I just talked about. And we are going to write down exactly what I want you to do when checking for the CLT. So we're going to check the conditions. Can I help you? Oh, okay. Thanks. Okay. Nurse wants to see. So, oh, I didn't pause it. Oh, well. Anyway. What is the first condition? Look back at your notes. What did it say? Random sampling. So, we're going to say, was the sample collected randomly? It says it in the problem, therefore we have to assume it to be true, right? So we're going to say the words literally, sample was collected randomly. If it did not say that in the problem, we would have to say the words, we assume the sample was collected randomly. Because often it doesn't tell you in the problem if it was or wasn't. What's the second condition? Independence, or if we don't have independence, we would say the 10% condition, okay? So are they independent of each other? Right? We don't know. But what we know, not here, because if we don't know independence, what do we do instead? The 10% condition. So what we would say is, what's our sample size? 16. So we would say 16 is less than 10% of, and this is where we put context in. Erica, make sure you're awake, darling. Okay? 10% of the soft drinks bottled at this particular plant. Okay? So 16 less than 10% of the soft drinks bottled at this plant, I guess. I mean, we are assuming that they make more than 160 cans of soda, right? I mean, that's safe to assume that. All right, and then what's our third condition? Large enough. So one is the population already normally distributed. Does it say that in the problem? It does? Ooh, it does, doesn't it? It already says it. So guess what? I don't care what the sample size is, do I? Don't care. So we can say that the population is normally distributed. So what can I do? I can use my CLT formulas. So how do I know that I'm talking about an average or a mean of means that already exist? Read the problem. So it says here, what's the probability? What's the probability means? Gosh, I hope it's either binomial because I can use binom CDF. Maybe it's geometric because I know how to do that. But gosh, if it's awesome if it's normally distributed because I really know how to do normal distributions. Okay? So what's the probability? So I'm thinking, okay, maybe it's normal. Let's hope. That the mean volume, the average volume is between, the average of the samples, okay, is between here and here. So let's go ahead and figure out what is the mean of the means. What would it be? Are we given a mean? On average, it says on average contains 12 ounces of soda. Right there, on average, right? So that would be, so the mean is 12. What is the standard deviation of the means? No. There you go. 0.16 divided by the square root of our sample size, which was 16. So 0.16 divided by 4 is, oh, oops, just 0.4, right? There we go. 0.04, thank you, Zachary. So we're going to use this information here in our normal distribution. Okay? So I'm going to draw a picture of it just so we have a clue. The mean is going to be at 12, right? And we're looking for the mean to be between 11.96 and 12.08. Okay, so this is what I'm looking for. And if you look at your standard deviations, do we even have to do normal CDF? Can we use our empirical rule if we wanted to? Because isn't it within one standard deviation on the left and 2 above on the right? Okay, so we could use our empirical rule if we wanted to. But we'll go ahead and just use our calculation that we know. So we have normal CDF, our lower bound, our upper bound, our mean, and our new standard deviation. And tell me what you guys get. Let's round to the nearest 10. So we would say 3 decimal places. So 0.816. Did y'all get that? I'm looking over Sean's shoulder here. Or type it in. 816? No? Uh-oh, what did I do wrong? Okay, I just was upside down looking over someone's shoulder, so I totally agree. So we have 12 and then 0.04, and we got, 0.819. I agree, okay? Excellent. So pretty likely, okay? So we have a pretty good probability that it would be between those two values. I believe it was the problem. Okay, sure, no problem. Any other questions?
Do we have to include the 1, 2, 3?
Yes, always. Ask that question again. It's a good question.
Do we have to include the 1?
Do you have to include what I wrote in blue? Abso-positively. Okay, you must check your conditions. Always, from here on out, pretty much the rest of the year. Yes. You can watch the video. No, it's fine. Just check your conditions. We found our new standard deviation, right? Sample size divided, the standard deviation divided by the sample size, square root of the sample size. And then we just drew the normal curve, and then we found the probability given it. But we had to use our new mean and our new standard deviation. And we were able to do that because our conditions checked. Okay? All right, let's try another one. Okay. By the way, let's just look at these questions real quick. I'm going to do a different context problem here because I want to make sure I get through enough. But What would change in this problem to answer this question? Right. So you would just redraw it. We still have a mean of 12, right? We have 11.96, and we're going less than, so it would be down here. But wouldn't we still use our mean and standard deviation that we just found? Okay, just making sure. Right. What would change here? The standard deviation now changes, because originally we had how many Coke bottles? 16. Now we have 25. Is our standard deviation going to get larger or smaller? Smaller, because it's got a bigger sample size. So you're dividing by a bigger number, right? So it's going to get smaller, which is a good thing. And then what happens here? It's even smaller, okay? And that's what we're deciding. What's changing is just the standard deviation in each of those cases. Okay? Good. All right. Here's the last example I wanted to talk about today. Let's look at this one. Whew, let's turn a fan on. In this particular question, you always want to start off, is this a means or a proportions question? Okay, how do you know? So we're looking for keywords, clue words, right? Average is one of those keywords. Would you agree? Okay, so if it's talking about an average or a mean, then we know we're dealing with the central limit theorem like we know, the formulas that we're dealing with. What might give away a proportion problem? What would be a proportion? Give me an example. Wake up. Come on, y'all. I know it's warm. A ratio, a percentage. What if it said 33% of hot dogs have this? Wouldn't that be a different kind of a question? Okay, so if you're either given a percentage or a proportion or something along those lines, then we have a different ball game, a different set of formulas, a different set of conditions, okay? So right now we're talking about average fat content, okay? And we're going from here. So we're going to check to see if the central limit theorem applies. What's my first condition? Random sample. What does it say that it was? It just says a random sample of hot dogs. So it says it was collected randomly. Now, I'm not sure I believe it because, you know, us statisticians, we have kind of a ruthless eye. And I don't know, you tell me it's random, but I bet you just asked your friends or something like that, right? So who knows? But we'll say, okay, it tells me it's random, so we're going to say that the sample was collected randomly. And make sure, Sammy, that when you write these conditions, I can read it. Okay? All right, number 2, what am I checking for? Either independence or 10%, either one. It's really hard to prove independent, so more often than not, we're looking at the 10% condition. So what will we say here? What's the sample size? 36. So 36 is less than 10% of what? So whatever this particular hot dog manufacturer makes, right? At that particular manufacturer. 36 is less than 10% of all hot dogs made at this factory. Okay, and then the last condition? Large enough. So in the previous example, we were told initially that the population was already normally distributed. I don't believe we're told that here, are we? No. So what do we have to have? So is it? Yes. So we can say that, I'll just write the large enough, and I'll put a question mark. And I will say 36 is greater than 30, therefore the CLT applies. Is that enough shorthand for you? Okay, good. So we've checked all 3 of our conditions. We're clear about what the conditions are. Please don't write random check. Okay, that's not clear to me what you're doing. The sample was collected randomly. That's what you need to say. Okay? And then you need to be very clear about what is meant by the 10% condition. Use the figures. Use your sample size. What is it greater than 10% of? Be contextual. And then large enough, the last one. So let's find our mean of our means, and let's find our standard deviation of our means. So are we given something? Okay. So we're told that the mean is what? 18.4. And it doesn't change, does it? It's just the standard deviation that changes. And are we given a standard deviation? 1 gram. So 1 divided by the square root of 36, which is 1 divided by 6, which is 0.16 repeating, 0.16 repeating. Okay, which is obviously a lot smaller than 1. We expected it to be smaller, didn't we? Okay, good. So we're trying to figure out, does it indicate that the manufacturer's claim is incorrect? So let's make sure we understand how we could answer that question. So the mean average that we got from our sample was 18.4, right? But they claim it's 18. It reminds me of a Seinfeld episode. I'm probably showing my age. Y'all even know what Seinfeld is? Okay. There was a Seinfeld episode many moons ago about the yogurt and the fat content of the yogurt. If anybody watches it, this is the same kind of this. Okay, anyway, I'm old. That's fine. Huh? You're more of a Friends watcher? Yeah, well. Maybe I'll bring it in and I'll show you about that. That would be a good thing to do next Flex. Maybe I'll actually do that. See if I can. That's a good idea. Anyway, so in order to answer this question, we have to decide here, well, we know it's a normal model. We know the central limit theorem applies. Do you agree? So let's kind of draw it and sketch out what this might look like, and then we can kind of see if we can prove them wrong. So when we draw this, we have the claim as 18, right? Okay. And then we got 18.4. Would you agree? Okay. So what we're trying to figure out is this unusual? Is an 18.4 an unusual figure? So what we're going to do is we're actually going to say, okay, if we're trying to prove the claim incorrect, yes?
Is there kind of like a close enough thing when it comes to this?
What do you mean by that?
Like if it's close enough.
Well, that's exactly what we're finding. Okay, is 18.4 close enough? That's exactly the same thing that we're finding. Good question. Perfect. Different way to say it. We're not sure. Okay, but what we can find is what's the probability that I would get something like 18.4 or even larger? What's the likelihood that I would get something that's even bigger than what I got? Are you okay with what I'm saying? If that probability is really, really small, is that a good thing? Yeah, it actually is. We want that to be a very small likelihood, because if it's a very small likelihood, that means that 18.4 is probably not that unusual. Okay? So let's find this probability first. So what we'll do is we will say, okay, normal CDF, 18.4 to E99, some number far off to the right. We have our mean. We have our standard deviation. I'm just going to leave it as 1/6 so I don't round. And we'll go ahead and figure out what we get here. What is that probability? So I didn't, 18, sorry. And then we had 1/6. 18 is the mean. That was the claim. 18.4 is what we found. That's our sample. All right, and we got 0.008. What does this mean? It means that, I'm going to write it down because I have it written in words. It's probably a good way to, I don't want to say it wrong, okay? It means that there is, let's try, there is a 0.8% chance, right, that the mean, the true mean, the true average is greater than 18.4, right? Very unlikely. Therefore, there's not enough evidence to overturn the claim. I would. Now, what we have actually found is something called a p-value. And we're going to, in the coming weeks, talk a lot more about what a p-value is. But the idea is you want a p-value to be very, very small. The smaller the p-value, the likelihood that we can't overturn the claim. What?
My father works with this all the time. He works for the plant variety of fiction office. What he does is he compares the data sets of two different sets of plants, trying to decide if one is actually different from an already established variety, and he looks at the p-tests all the time.
Yeah. I mean, it's a very common practice, right? Okay. So, good. How do we feel about it? Okay, so far? Yeah. Okay. Don't worry too much about the idea of a p-value. Okay, that's okay not to understand at this point. But making sure that we can answer the question as, did they make a claim and we got a sample and our sample's wrong? And actually, this kind of happened in truth with M&Ms. I think I've told you that they used to have a big website where they talked about the proportions of the number of colors and blue and green, and us stats teachers got kind of like ornery about it, and we kept proving them that they're wrong. Well, our sample says no. You know, you don't have 25% blue, you know, whatever. So anyway, this is the same kind of idea here. But again, we did means here, and then there's proportions that we're going to talk about next class, okay? So what I'd like for you guys to look at, and there's no blue sheets, by the way, okay, is just these few problems, okay? And there's a 1, 2, 3, 4, 5. And actually, the first couple are just kind of like writing the formulas and that kind of thing. There's really not a whole lot to them. But the last couple are contextual situations that you'll have to check your conditions. I'll be looking for the conditions to be checked, as well as basically what we did today, drawing the normal curve and all of that. Okay? Yes. Like I said, next class, I'm going to be checking for the just checking along with these problems together. Yeah, if you want me to, you'll find it.